Okay, so the next speaker is Mark Handover of Mentor Graphics, who's in Bristol today. His talk is on automating assertion-based verification, automating ABV. Mark has been involved in the design and verification of complex SOCs for over 15 years, 11 of which have been in his current role with Mentor Graphics. He has expertise in formal and assertion-based verification. So we'll hand over to Mark now.
So I'm going to spend the next few minutes talking about a solution from Mentor called Questa PropGen. So as Mike said, this is a solution in the space of automating assertions themselves, so creating the properties automatically for you. So the concept of assertions and properties have been around for a long time now. Zero In, amongst others, were doing assertion synthesis and creating properties from RTL way back in the late 90s, early 2000s, even before the advent of PSL and SVA, and then of course there's OVL. So they've been around a long time, and it's well documented and I think well understood now about the benefits you can get from these. So, you know, assertions basically document your design, allow you to describe the intent. You know, this is nothing new. They increase observability, so you get quicker time to bug effectively, gives you better bug localization, and therefore faster time to reason about the problem and fix the issue. So all this is well understood, but what we see generally in the industry is assertion take-up is still pretty low. So some companies, as we've seen here today, Freescale and ARM do a lot of assertions. Others do some, and there's still some companies out there who do none at all. It's very patchy in some places. It's like medicine. You know, we know it's good for you, but people don't always take it, and there's a number of reasons for that. These are just some of the more commonly kind of quoted reasons for not writing assertions. People are just too busy. I need to get my job done, and I haven't got time to write the assertions. I'm too busy debugging is typically the case. Whereas if you actually use assertions, you won't be so busy debugging probably. There's a duplication of effort. So, you know, you're trying to describe your design intent here, and you're writing the RTL, which is obviously formulating that intent. So there's a perceived kind of duplication in effort there. That may be more of a methodology issue. There is a maintenance issue. You write assertions to check your RTL, you write the RTL, you change your RTL, your assertion could now break. So there's a maintenance effort involved there. But fundamentally, writing assertions is not easy. If you're a design engineer, a verification engineer even, it's a mindset thing. It's a different concept, it's a different approach. It's another language to learn for one. But writing assertions is not particularly an easy task. And so what Questa PropGen does, which is the solution we're going to talk about, it tries to automate this. It tries to remove these roadblocks, tries to make the medicine more palatable, should we say, reduce the bad taste. So this is how it works from a high level. So we have Questa PropGen over on the right-hand side. You take your RTL, you take your existing testing environment, so you test bench, test suite, and you simulate, and you will be capturing waveforms of some description, be it, you know, pretty exhaustively or a subset of them. And then Questa PropGen consumes those trace files. So you take the waveform files, you take the RTL, and PropGen will look at the waveform files, look at the stimulus within them, look at the structures in the RTL, and it will produce properties. So it captures your design intent based on the stimulus in the waveform file and the structures that exist in the RTL. And of course, you could take those properties back to simulation. Probably not worth taking them back to the same simulation with the same tests. They're only going to verify what you've already have. But if you have modified RTL or you have a different suite of tests, you could plug those assertions straight into the simulation environment. But it also opens doors to other technologies. You need properties for formal, so you could then take those properties and drop them into a formal solution. You could increase observability on your emulation platform, so it was mentioned earlier. So this would be one door to do that. So assertions give a picture or a representation of your design intent, and to do this there's kind of two aspects, I guess. One is to exhaustively describe an RTL block you need a fair number of assertions, but also you need different types of assertions. You need a richness in your property set such that you can describe all the different behaviors therein. And so the idea with PropGen is we don't actually produce just one type of assertion. We have layers of assertion to build up this design intent, and we do it on a basis where we can generate lots and lots of properties. So at the signal level, you may have things that reason about counters, different types of encoding, values of your signal, so ranges, constants, whether they're driven to X in your simulation. Then we have assertions or properties around implication and time. So if A happens, then B should happen, or if A happens, then B should happen in some time frame. So you can have temporal delay in there. We can also have a kind of higher level view, so we can look at macro instances in your design, such as FIFOs, handshaking behaviors, recact checks, pulse width checks, these type of things. So we're coming up beyond the low level. And as we build up these layers of properties, we give a more and more accurate of the design intent and build up a better picture of your design. So let's look just briefly at the flow. So how does this really work? So we take the RTL, we take the trace files, be in whatever format, and as I said, you drop these into PropGen, and PropGen will look at this, form properties based on what it sees in the stimulus files, in those waveform files, and what structures it can find in your RTL. And then there's probably a list after we've generated the properties, a step or other of going around. So steps 3 and 4 here. Step 3 is reviewing the setup. So ultimately you'll want to just check that PropGen is doing the right thing, that it's doing something sensible, that it's focused at the blocks you were intending to focus on, that you've got clocks and resets looking sensible, all these kind of things. So there'll be probably a cycle of going around tuning the setup of the tool potentially. But then number 4 is actually to review the properties themselves. So there's almost certainly going to be some kind of review, sort, explore phase that you go around. And we'll look at this briefly on the next slide as well, where you just go through and you classify the properties. You may want to drill out different sets of properties. You may want properties of a certain focus or a certain type. So we can do that. And then ultimately you drop out the bottom and we export assertions for you. So these will be in System Verilog, and we generate properties on a per module basis, so they're partitioned, and all the binding code is there as well. So you just take the assertions, probably the ones that you've gone through an exploration phase of, you drop out the assertions and you can then compile them for simulation, formal, emulation, or whatever platform you're using. So let's just look at this this review phase. So as I said, there's we generate potentially thousands of properties for you. Do you want to use them all? Maybe you do. Maybe you want to refine them a little bit. Maybe you want to sanity check them. Maybe you want to export a set that are focused on particular areas of your design. Maybe there's areas of code which is changing, and you want to focus on those areas. So you'll go through probably a kind of review process where we generate the properties. You can load them up in the UI, and there's also different ways to flip them and look at them here. So you can look at them on signal type, condition type, property type, and various RTL views as well. And the idea here is you look at them and you decide, okay, which ones are more valuable to you, which ones make more sense. So there are certain types I'm interested in. And one of the ways you can do that is with ranking. So the tool will automatically rank the properties it generates per module based on activity and distribution. So if it sees a signal with a high level of activity in the waveform view that propagates everywhere, then it will give it a higher rank than something that doesn't, that has low activity or very little distribution. So the kind of supposition here is that the higher rank is more important, but you can change this, and you can, as I said, tune this view to whatever you want. And then you go through here and you mark some as keepers, and you mark some that you're not interested in and can be thrown away, and you end up with this subset. And then this is the useful targeted subset that you're going to take forward onto some other platform. You could actually use formal as part of this kind of review step. So you could take the property set and you could throw it into formal, and if you get proven properties, then these are invariants. They're never going to fail if you don't have any constraints, or won't fail within the realm of those constraints. So these you could actually just chuck straight away. If they're never going to fail, they're proven already. Then there's no point in loading those onto some other platform maybe. The other thing is fire properties. So fire properties could be due to a number of things. So there could be a design bug. So you had a simulation running, you use the trace to generate the properties. If they now fail in formal, it could be an RTL issue. It could be a coverage hole. So this may be an area of your design where you're not exercising very well in simulation and almost found a corner there. Or of course it could be unconstrained inputs within the formal space too. Formal has an application here potentially in the review phase. So we're going to generate properties, and there's obviously a number of uses for these, a number of places where these could be used. One of these is actually just within the review phase itself. So you're running known good simulation here to produce these properties. So the question I get asked a lot is, what's the point? I'm generating properties. I need to have a good test bench to start with and stable RTL. What's the point in generating properties from those? Well, we're going to see a few use cases for these on the next few slides. But actually during the review phase, it can actually show things about the design that you supposedly have stable, that supposedly have a good coverage set for already, a good test set. And so if we take just this example here, so you have the property set, you're reviewing it, you come across the FIFO, and there's a couple of aspects here. So based on the simulation traces, the tool could never see behavior where there was a simultaneous push and pop FIFO. If the FIFO was designed to allow that to happen, then there's an issue here. It could be a coverage hole, or it could be a bug. Either way, it needs an investigation. And the other area is with depth here. So during the simulation trace, we never filled the FIFO beyond 12, but it was spec to 16. So is this an overspec FIFO? Is this a bug? Is this another coverage hole? So it can lead you to reason just about the design that you're currently testing anyway. Let's look at some other cases. So perhaps a few different varieties of ways you could use these properties. So the first is a kind of IP-based model, if you like. So you may have some IP, it may be legacy IP with no properties, and you want to add properties to it. So you could be reusing it. You could be reusing it and modifying it slightly. So there'll be a case to generate maybe some properties to help in the verification of that. It may be one area you're modifying and you don't want to break everything else within that IP. It could be a case where you are an IP provider, and so you're shipping this IP to your customers. It doesn't have properties in it, and they're constantly calling you and asking you for support because of the way they've configured it in the final design. So you may now want to ship properties with it, and this may be one way we can do this. So you take the IP, the DUT here, you run the simulation tests you have, you drop it through PropGen, and the properties come out the bottom, and you can then do what you wish with those. So at the IP level, you could take those properties and just bubble them up to the SOC level. And so now you have characterized IP, if you like, in terms of behavior to check at the SOC. As I said, you could ship these to the end customer. If you have unmodified RTL, so you're taking this legacy piece of IP and you're taking it through and you generate the properties and you're just reusing it, perhaps we could assume it has high coverage in the original tests, and you thought it was exhaustive, and it's maybe been proven time and time again on other projects. So maybe we don't even need to review these properties now. We're going to assume they're good properties, and they can just be shipped as are. But if you obviously have modified the RTL, then you need to maybe go through that review phase again and again to get some more useful, sensible properties out. So if we've taken these properties and we've shipped them, or we've characterized the IP and then we're reusing them at the SOC level, what happens if we see a firing? What does it mean? So maybe we're in simulation or emulation and we have these properties and we'll see an assertion firings. Well, it could be a few things. It could be that the IP behavior violated in the SOC level. So you have describe the IP, you characterize it in the properties, it's now violating when it gets to the SOC. So that could be an IP bug. It could be a configuration issue. So it could be that we're not using the IP as it was intended, so it's not configured correctly in the end target, the SOC. It could be a coverage hole at the IP test level. So perhaps we're running tests at the SOC to functionally test everything including the IP, but we've uncovered a coverage hole where we didn't fully test the IP at the lower level. So it could be a few things. If you don't see any firings, basically it's meaning the SOC didn't validate the IP behavior. So the IP is being used as you intended it to. And you're not exercising any behavior at the SOC level that you didn't already test at the IP level. So you can probably assume it's good. But ultimately, you're increasing the observability here. You're improving the observability and the debug capability and coverage at the SOC level. And obviously, in emulation particularly, this can be very valuable. If Here's another case, slightly different one. Let's assume we're running some RTL with some test suite here. Let's assume we're running the simulation this time, and we run the two together and we're passing, so everything's good, and we're happy. Now we want to ship this or put it onto an emulator, so we want to run even more system level tests. So we take the same RTL, we take the same test environment, and now we run an emulation, but now we're getting failures. And this is not uncommon to see this kind of behavior. So the problem here is, okay, we have a mismatch in behavior. One's passing, one's failing. Where do we start? Which one do we debug? Which one is wrong? Where do we investigate first? So again, we can start using PropGen to help in this space. So we can take the passing environment, simulation in our case. We can take the RTL and test, produce the path waveforms, capture the stimulus file, and then take that with the RTL through PropGen to produce our property set. And then we take the property set. We probably want to go through some review phase, particularly if we're hitting an emulation platform where we have probably limited resource. We don't want to take 20,000 properties through or something. So maybe we want to focus in on an area. Maybe we have an inkling as to where the bug was or the problem behavior or module, so we can focus some properties there. So we go through a review phase and we end up with some debug property set. And then we can take that debug property set onto the failing platform, so emulation in our example here, and then run it through, and obviously it still fails, but now we have failing assertions, which we can use to help debug the problem, to narrow down, to understand whether it's some kind of setup issue or a real problem in somewhere else in the platform. And then finally, we have an application here for formal. So beyond what I said earlier, which was kind of using formal or abusing formal in the review phase, we were talking about if we formally prove properties, they're going to be true for all stimulus. So if you have no constraints, then they're true. If you have constraints, they're obviously true for all stimulus within those constraints. But they're creating invariants here. And if we have a block which we're trying to test with formal, and we're hitting some inconclusives, we can take those invariants and use them as helper assertions. Okay, so now we can try and use those as assumptions. So use those proven invariants, use them as assumptions, and then go after the inconclusives that we're seeing on our formal platform, just to try and help the algorithms to get convergence or closer to it. There's a couple of other models that we could do. So maybe we're running formal and it has some standard interface protocol or some protocol on the interface which we don't have constraints for, and we don't want to manually write them. So maybe we could use PropGen to learn the protocol intent from simulation. So we're simulating, we're stimulating that interface. Let's go and grab the behavior and then create the assertions and then use them as constraints in formal. Or slightly different, we may have user constraints and we want to make sure we're not over-constraining, so we can take those generated assertions and then try and run on them in formal with our user constraints. And then we'll soon see things like vacuous proofs or vacuous issues, which would indicate that we're over-constraining our design and our user assertions. So just to summarize, so this is PropGen. So we're trying to help reduce that problem of taking the medicine. Okay, we're trying to make it easier for users to get access to the benefits of assertions. So we know the benefits are to increase observability ultimately, document your intent, and driving up quality. So this is trying to reduce the barriers, trying to give you access into some of these benefits. PropGen, as we saw, produces a range of different property types to try and accurately reflect the full intent of your RTL. We can use them, they're SVA, so you can use them in simulation, emulation, formal, or anything else that you can think of that would consume SVA properties. And there will be some aspect of reviewing, filtering, classifying, and hopefully we've come up with a reasonable way to do that through our intuitive and easy to use UI. Thank you.
Any questions? This is going to be a tricky one. I'm still on between, so you can have a mic then.
Yeah, this is Isidoro from Infineon. So it looks like a quite automatic assertion generation. I was wondering what is the chance that some assertion generated is just a consistent wrong behavior of the design, and so like what's happening that then so we should consider the review process as something that need to be done.
Yeah, if you have failing, so the idea is you run on passing assertion or passing stimulus files, right? So you need a good simulation, like we were saying, to start with to generate these. Yes, if you have bugs in there or you're somehow simulating some bad behavior and still passing your test, then you could end up with assertions that reflect that. True. Yeah, we're just taking the stimulus as is with the RTL and generating or formulating these properties for you. So the review phase is important. Yeah.
Yeah, a question from me as well. Quite often these tools, they generate a lot of white noise, so the review stage can actually be quite difficult because there's so many assertions. Is there a solution to that or not?
No. I mean, yes. Yeah, I've seen it generate thousands of assertions, and not all of them may make. They all should hopefully be accurate. If you have passing good high coverage simulations, then the assertions should all be accurate and reflecting behavior. But some of them may be, not very valuable, should I say. There'll be some which just say this should be a constant, for example, and if they're on config registers or modes or things like this, then you may just want to throw those out. So the idea of the review step is, or what we've tried to do is give you enough tools within that step inside the UI to look at the properties in enough different ways that you can drill out more interesting ones or more valuable ones, more high value ones, shall we say, and that's kind of where the ranking comes in.
Okay, thanks, Mark. There's one question online from Baz Arts. As long as your RTL is under development, you continuously have to review your properties. How does this effort scale with big SOCs?
That's a good question. But that's no different than writing properties yourself, right? At least this is quick and easy, and you can hit the button. If you were writing your own properties, then the maintenance effort is much higher. But yes, if the RTL is going through development, then you have to wonder whether you want to be generating them at that step or not. And certainly you may want to target them more, so generate them for sub-blocks and then build it up gradually in a more kind of modular fashion as things become more stable.
Okay, thanks, Mark. We're going to go to Grenoble now. Matthew, any questions in Grenoble?
No question in Grenoble.
Okay, thank you, Matthew. And Sophia, is it Ted or Laurent? I don't know who's chairing there. Oh, Pierre. Sorry, Pierre. Any questions from Sophia, Pierre?
Okay. No, we don't.
No. Okay. Okay. No more questions. Sorry. Oh, sorry. Ashish, any questions for imagination? Any questions for imagination?
Hi, Mike. This is Ashish. Quick question for Mark. You were talking about extracting invariants and so on. So usually invariants are meant to be true properties of the reachable state space. Because your extraction algorithm works on the existence of a simulation database, how reliable is your invariant extraction? Do you have any thoughts on that?
Yeah, hi Ashish. So they should be accurate. I mean, what we're doing is, I take your point, we're generating from a simulation space, but what we're saying is if you take that assertion, even if it doesn't fully respect, so say it was a range check or something, and we were observing a certain range, but it went beyond that. If you can prove that exhaustively in formal, then that should form your invariant.
So you're basically talking about extracting boundary checks on
more, I think,
smaller
yes.
components.
Okay.
So I was just going to say this could be done independent of this existence of a simulation database through structural analysis of the code, through structural analysis of the RTL.
Yes, you're right. More of an auto-checking route. Yeah. That's true.
Okay, thanks, Ashish. You've got one more question online. You're popular at the moment, Mark. It's from Anton Shank. Would the assertions generated work on different vendor tools, or are they limited to Mentor tools?
I'd love to say they were limited, but no, they're SVA. It's pure SVA, so LRM compliant SVA. So we generate assertions per module with all the binds. So what comes out of PropGen, you should just be able to compile whichever route you're using, whichever tool you're using, as long as it supports IEEE SVA.
Yeah, Anton, you can use whichever simulator you want. Okay, thank you very much, Mark. Thank you.